Hello, let's get stuck into some thermodynamics. Now, there's two priorities you got when you start learning this subject. So, first of all, we need to understand internal energy because that's what thermodynamics is about. So, we need to know where the energy is located inside different substances, whether it's solids, liquids, gases. So, we need to be able to describe that. The second thing is we need to get used to the terminology. There's a lot of terminology in thermodynamics. Some of it you'll be familiar with, some of it will be new, some of it will be words such as temperature and heat that you would have used since you were at nursery, but we'll have to start using in a more specific, scientific, and deliberate, careful manner. So these are the things that we need to get used to, and we're going to look at in this video. And we'll do this by taking a journey through the three phases of matter: solid, liquid, and gas. I mean, I know there are four phases of matter, really. You've got plasma as well. Plasma is this fully ionized or nearly fully ionized state of matter where the electrons and the nuclei of atoms have sort of been, stripped apart to a large extent, and they interact in very complicated ways. I mean, that's why there's a whole area of physics called plasma physics. This is way beyond what we're doing in any of this. So, because that's adding in new forces and energy stores and things like that we're just not considering in classical thermodynamics. So let's not worry about that. Let's stick with solids, liquids, and gases. Now, this also gives us a nice way in as well, because we already know some basic stuff about what's going on here. You start with a solid, you heat it up, it melts, it becomes a liquid. You heat it up some more, it vaporizes, it becomes a gas. You cool the gas, it condenses into a liquid. You cool the liquid and it freezes or solidifies back into a solid. So we know we've got some kind of hierarchy here where you're moving from we're moving from our solid to our liquid to our gas, and this is a case of energy in and then going back is energy out. So we know we've got something going on here. So at least we got a framework to start building around, and this is what we will do now. So I'm going to give a high level overview of a lot of the stuff that we're going to be talking about and how it fits in with changes of state of matter, as we're going from solid to liquid to gas and back again. And I'm going to introduce the terminology of thermodynamics as we go through it, just to make sure that we know how we're describing all of this. And I've made a start here by putting this energy scale at the top. Thermodynamics is about energy. So I've got energy increasing from left to right, decreasing from right to left. So if we're describing that, the first thing that springs to mind for most people, if you're putting energy into a substance, is they'll say, well, that's heating. And for taking it out, let's say it's cooling. And this is fine up until a point, but it's missing out a certain part of how we can get energy in and out of a substance. We have got these methods of heat transfer, the ones that we're familiar with, radiation, conduction, convection. So radiation is energy coming in as photons. The conduction is where we've got two substances in contact with each other, and we've actually got the movement of the atoms and molecules in the hotter substance transferring then their energy over to the cooler substance through direct contact of the atoms and the molecules, or at least as direct as it can be. And then we've got convection, which is more or less mixing of a particular substance in order to even out the energy throughout that substance. Now, that's all well and good. We have got those, and that's a really important part of it. But we have also got work as well. So we got work coming in for transferring energy in, and we got work out for transferring energy out. So this connects in with the first law of thermodynamics. So as in the one titled the first law of thermodynamics, that's the second one in the list, because they count the four laws going from 0 to 3 rather than 1 to 4, because they thought of the zeroth one after they had come up with the other three, so they had to stick it at the start. So the first law of thermodynamics is talking about this. So it's talking about these two different ways of getting energy in and out through work and through heat transfer, and how that is all conserved. You've got this energy conservation thing going on. So whatever we're putting in, we can get back out again. So you don't want to forget about the work side of energy transfer in and out of material. Right, now we need to tie all of this into state of matter. So as we've been saying, we got solid, we got liquid, we got gas, we got energy increasing as we go from left to right. And we need to be able to describe these phase changes between the different states of matter. So solid to liquid is melting, liquid to gas is vaporizing. Spell it how is appropriate for where you come from. The gas to liquid is going to be condensing, and liquid to gas is solidifying. Now, some people go for liquefying. Not a big fan of that myself, because is liquefying talking about solid to liquid or gas to liquid? It's got a certain ambiguity to it. So not so keen on that. But otherwise, this is fairly non-controversial, picking out those words. Now we want to link all of this in, the energy and the state, to internal energy of a substance. So our internal energy, which is really getting to the heart of thermodynamics now, of course, is going to be split between potential energy, kinetic energy, because all energy is one or the other. So what are we including and not including when we're talking about internal energy in thermodynamics? Well, first of all, we're not including the macroscopic stuff. So if we've got a block of ice, say, and that block of ice is moving through space, i.e. its center of mass is moving through space, like we're dealing with something in classical mechanics, and then we could calculate the kinetic energy of that. Well, no, we're not having that. That's not internal. That's not our microscopic energy. This is macroscopic, so we don't want that. Similarly, if we put this ice in a gravitational field, or we got some other potential energy kicking around at a macroscopic level, we don't want that either. So we don't want that bit. We don't want to go down, if we go down to the subatomic level, we don't want to look at binding energies inside the nuclei of the atoms inside the substance. That's too low level. We want the stuff that's in between. So we've got then two bits that we need to look at if we're looking at the microscopic level. So we've got the constituent particles which are making up a substance. So if it's a pure substance, everything that's in it that's making it up is either going to be atoms stuck together in some way. Like say you've got graphite, it's all carbon atoms that are just making up this graphite. Or it's going to be molecules that are going to be the repeatable part, the constituent element of the substance. So say it was ice, then it's water molecules that we've got that is all, making up what the ice is. So if we're looking at that level, at the level of the constituent element, then we're looking at the motion of those constituent elements. That's going to be our kinetic energy. So in a solid, it's going to be vibration about an equilibrium position. For a liquid, you're going to have translational motion going on. Okay, they're still held in place to some degree. That's why it's a liquid, not a gas. But they're moving around more freely, but you've still got that kinetic energy of motion there. They're not oscillating in the way they are in a solid, but we've still got kinetic energy. When you get to a gas, they're flying around all over the place, and we're getting closer to a classical mechanical description of how an atom or a molecule is just flying around in a gas. So that's the kinetic energy we're looking at. The potential energy, you've then got more or less a new type of binding energy, but rather than it being our subatomic nuclear binding energies, we've now got interatomic or intermolecular binding that's holding these things in place. So we've got a lot of binding in a solid, we got less binding in a liquid, and we got close to no binding in a gas. So that's the potential energy that we're looking at there. So that's the first part of it. You get a little bit of complexity that we're going to end up largely ignoring, but we've got a sort of hat tip to it, of if the constituent part is a molecule. So say it was ice, and we've got our H2O. So we've got our O, we've got our oxygen, we've got our two hydrogens. There's a structure to a water molecule. Inside that molecule, that is also going to have potential energies it's got the binding between the atoms. There's going to be certain stresses on the shape of the structure, potentially. There's going to be kinetic energy of the vibrations inside the molecule. Now, this is all included in thermodynamics. It's still thermodynamic energy. It's just much more difficult to describe. It's still included in our work in plus heating and our work out plus cooling. It's still all part of that, as in you heat an object up, you heat up some substance, some of the energy is going to go into the potential energy and kinetic energy inside the molecules, if it's made of molecules, in that substance. Now, you can put that in and you can take it back out again. It's just really hard to quantify, well, in general, but particularly when you're starting out in thermodynamics. We get a bit of a nod to it in specific heat capacity. It's one of the factors that changes the specific heat capacity from substance to substance. So we'll talk about that a little bit more in detail. But largely, particularly when we get onto ideal gases, one of the things that makes an ideal gas ideal is that we ignore all of that internal structure there inside a molecule. So that's the stuff that we're including. We're including the microscopic stuff for potential energy and kinetic energy, not the macroscopic, not the subatomic. So there we go. So now I'm going to add another scale at the bottom of temperature. And we're going to say, well, what if we started off then with our minimum internal energy? There must be some sort of low point that we can get to. This actually comes up, and I'm going to talk about this more detail in another video in the third law of thermodynamics. So say we're at our minimum internal energy. So what's going on as we then add energy in? Now, the third law of thermodynamics is putting our minimum internal energy at 0 Kelvin, our absolute zero, and that's also going to get a separate video on absolute zero. So if we started at 0 Kelvin, we got minimum internal energy, we've got close to zero kinetic energy, as in all of our atoms or molecules have pretty much stopped moving inside the substance. You don't get exactly zero kinetic energy for various reasons in quantum mechanics. You get a certain fuzziness in the location and motion of these particles, but we can say it's close to being zero and everything stopped moving. We've then got very, very negative potential energy because everything is as strongly bound together as it can be. If we think of other times we've dealt with potential energy, we set our zero potential energy at infinity. Think of binding energy, think of gravitational potential energy. You set zero at infinity, and then as you bind these things together, it gets more negative because you have to put energy in order to separate everything. So it doesn't take effort to bind things together if they're attracted to each other. So that's what's going on here. As they're most bound together, most tightly bound, we've got our most negative potential energy. So that's our starting point. We then start putting energy in. Our internal energy is increasing. The kinetic energy is increasing. The potential energy, this is where you have to start making some assumptions. If we're going to be ignoring the internal structure of molecules in the substance, we can kind of say, oh yeah, the potential energy is staying constant here. We've still got these intermolecular or interatomic bonds inside the solid. They're not really going anywhere. All we're doing is making the atoms and molecules vibrate more. We're increasing their kinetic energy. The potential energy isn't really changing that much. The temperature is going up as we're doing this. And this carries on until we've got enough kinetic energy that the atoms or molecules start breaking the bonds between them. They've got enough kinetic energy to start moving from a solid where they're tightly bound in place to a liquid where they're less tightly bound in place. Now we're getting a phase change. When we get this phase change, okay, the internal energy is still going up because we're still putting energy in, but now we're getting a change in the bonds. So the atoms and molecules are becoming less tightly bound, so their potential energy is going up because they're becoming less negative. Now it's just negative when you get into the liquid compared to the very, very negative that we had in the solid. So the potential energy is going up, but that's where the energy is going into breaking these bonds. The kinetic energy isn't changing, and the temperature isn't changing because, as we'll see in more detail in a later video, the temperature is connected to the kinetic energy. Temperature is a measure of the average kinetic energy of the particles in the substance. Now we've made it into liquid stage. Oh, actually, one thing I should mention there with terminology, because the temperature isn't changing, looking at the thermometer, you think, where's all this energy going? Temperature's not going up anymore. It's been going up, 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 up. Now you're still putting the energy in and it's staying constant. So you get this thing called latent heat. Latent as in hidden. So we've got latent heat here, and you can't really see where the heat is going because it's all going into this potential energy. So this is latent heat of fusion, because we're talking about the transition from solid to liquid. If you go from liquid to solid, another way you might describe that is fusing. I've gone for solidifying up here, but you're fusing stuff together into a solid. So we got that latent heat of fusion, and you get latent heat every time you're putting energy in, but the temperature isn't changing. Now we're in the liquid phase or liquid state. People use state and phase quite often interchangeably. If you really get into the detail, you can have multiple phases for the same state. So you can have multiple phases of ice. They're all solid, but different phases. We talk about phase change, going from solid to liquid, liquid to gas. And sometimes people will say, oh yeah, they're the phases of matter. It's not that bad to call these things phases, which is why sometimes I keep using the word phase rather than state. Anyway, if we're in the liquid state, we've got much the same thing happening again. You put more energy in, now we've got the kinetic energy going back up again. The potential energy is staying the same. The temperature is going back up because the kinetic energy is going up. We hit a new phase change as we go from liquid to gas. At this point, we've now got latent heat of vaporization. And same things happening here, where the kinetic energy will be staying the same, the potential energy will be going up, and the temperature will be staying the same because the kinetic energy isn't changing. When we get to our gas state, the potential energy is close to zero. If it's atoms, you can good as say it's zero. If it's molecules, you're still going to have some potential energy inside the molecules in the gas state. So, much as we've said, it's almost zero for kinetic energy at absolute zero. It's almost zero for a gas. For an ideal gas, it is zero. You're putting more energy in, internal energy is still going up, and we're back onto kinetic energy going up and temperature going up. So we've got this stepwise approach. If you were going to draw out a graph of temperature for energy going in, then you're going to have an increase in temperature till we hit a phase change. It's then flat for our latent heat. Then it's going to increase again when we're in the liquid state. Then we're going to get flat again for a latent heat of vaporization. Then we're going to have a temperature increase again. And the gradients of these slopes are going to vary because that is going to reflect the specific heat capacity of the substance in that particular state of matter. And that varies. Specific heat capacity, this is the amount of energy you have to put into a amount of substance in order to get a certain temperature change. And the specific heat capacity changes from substance to substance and for a particular substance depending on what state it's in. So the specific heat capacity of ice is different to the specific heat capacity of liquid water. So you're going to get a different rate of temperature change for the same power input. So this is what you're going to see. You're going to get these stepwise changes where you've got slopes mean kinetic energy change, flat bits mean potential energy change. So this is covering pretty much all of the terminology that we're going to be dealing with. There's a lot of it, and you need to be clear about how you're using these words in thermodynamics. So there's a lot going on here. Now, we're going to be building assumptions around a lot of this. We're going to do a lot of work on ideal gases where we're making that assumption of zero potential energy. That's why we're picking ideal gases, because it's so much simpler than describing solids and liquids. So, but there are other things we need to clear up before then. We need to have, I've touched on a lot of these laws of thermodynamics. We need to pick at those a little bit more. I'm going to start off by looking at temperature versus heat and how we go about setting up these temperature scales. So that's going to tap into the 0th law of thermodynamics. It's then going to lead us into absolute zero and the 3rd law of thermodynamics. And then we're going to start looking at evolutions of systems in terms of entropy and tapping that into the 2nd law of thermodynamics. So we've got a lot of work to do before we get on to ideal gases, and we need to look more closely at specific heat capacity. So there is a lot in thermodynamics, and these are very complicated processes. If you really want to be describing how a liquid behaves, man, that is difficult. Same with a solid. I mean, gases are tough, but they're the easier ones of the options that we've got. So I'll leave that there for now. That's given an overview again of how we're talking about things inside thermodynamics.